Space and time complexity can define the effectiveness of an algorithm. While we know there is more than one way to solve a problem in programming, knowing how the algorithm works efficiently can add value to the way we do programming. To find the program's effectiveness or algorithm, knowing how to evaluate them using space or time complexity can make the program behave in required optimal conditions. Doing so makes us an efficient programmer. Hey everyone, I'm Weber Khandelwal and I welcome you all to our Simplilearn's YouTube channel. Today, we will talk about data structures and algorithm complexity. But before we begin, let me tell you guys we have our daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for the latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit the bell icon to never miss an update from Simplilearn. Now, without any further ado, let's get started with the agenda for today's session. We will begin our session with a discussion on what is complexity. Then, we will discuss the big O notations. Finally, we will wind up this session with a discussion on various time complexities with examples. Now, let's get started with what is complexity. Complexity is a measure of how the resources, in this example, time, fluctuate as the problem grows in size. An algorithm may run quickly and show no time difference, but when the input size rises, the program may take longer to execute. It may become sluggish and perform poorly. Next up, let's discuss the big O notation. In theoretical terms, big O notation is used to examine performance or complexity of an algorithm. Big O notations examine an algorithm's upper bound of performance, that is, its worst case behavior. Big O notation also considers algorithm asymptotic behavior, which refers to the method's performance when the amount of the input climbs to extreme big. Computational complexity asymptote big O of f measures the order of employed resources based on the magnitude of the input data, that is CPU time, RAM, etc. As you can see in the graph, here is line graph to represent various complexities. We started with constant complexity to logarithmic, linear, square, and n-log complexities. Now, let's have a look at the various complexities. First up, constant time complexity. If the method time does not vary and remain constant as the input size increases, the algorithm is said to have bigger of 1 complexity. The algorithm is not affected by the size of the input. It takes a fixed number of steps to complete a particular operation, and this number is independent of the quantity of the input data. As you can see in this code, each statement represents 1. So when you count all of them, it gives us a constant amount of 4 or 1. Let's go to the code editor and try this very code. Let's make a function static void const t complexity. In this, I will have int a is equals to 100, int b is equals to 50. Then I will have another int sum is equals to a plus b. Then I will have write console dot right line, and then I will print out sum. Now let's go to the main program and call this function. So const complex, this is, let's save it and run it. As you can see, it is printing 150, which is sum of A and B. Now let's get back to our slides. Next up, log n complexity. A method with complexity of big O for input size n, where n is really big, divides the issue into little bits for each iteration log n. It takes log n steps to execute a particular operation on n items, where the base of the logarithm is usually 2. Because the base of the logarithm is not critical to the order of the operation count, it is frequently ignored. To explain this further, typically a binary search function has a big O of log n complexity. We can try this function in a code editor. Let's start with function creation. So static int bsearch. Its argument as int with braces space arr comma int x. Then in the definition I will have int l is equals to 0 and r is equals to length of the array minus 1. Now we will write a while loop l is less than equals to r. We will have int m is equals to l plus in braces r minus 1 r minus l divided by 2. This m is a pivot. Now we will check if x is present at the mid. So to do that, we will have if in braces arr in braces m is equals to x. We have returned m. This will only return m if it is at mid. Now let's say if x is greater than, then we should ignore the left half. So if arr bracket m is less than x, then l will be equals to m plus 1. Now here we have increased our lower bound to mid plus 1 so that the scope will shift from the left hand side of the mid to the right hand side. Now let's say if x is smaller, then we should ignore the right half. So we can write it as else, because that's the only other possibility of the left counter side. So now we will have r equals to m minus 1. Now we have decreased our upper bound from whole array length minus 1 to mid minus 1. Now let's say if we reach here, then the element was not present. Then we will be returning minus 1. This while loop will loop around this code until it finds the element. If it doesn't find it, then this will return minus 1. Now let's write the main block. Let's define an array int arr is equals to 2, 3, 5, 7, 11, 13. Let's have another variable int n, which will store the length of the array. Then int x is equals to 7. This will be the number which we have to find. So now int res is equals to b search arr, x. Now if res is equals to minus 1, that is we didn't found the element, so it will print console dot write line element not found. Now let's say we found it, then else we will have console dot write line element found at plus index plus res. Let's save it and run it. As you can see, it found the element at index 3. Since our element was 7, so it should be at 0, 1, 2 and the 3. Now let's get back to our slides. Next up is linear complexity. When an algorithm executes n steps for an input of size n, where n is a very large number, then The time consumed by the process changes linearly as the input size rises. The algorithm is said to have a big O of n complexity. To execute an operation on n items, it takes about the same number of steps as the number of elements. Linear complexity denotes a relationship between the number of components and the number of steps. Here is a simple program where we are using a simple for each to represent a loop. A typical loop will have an n complexity or a linear time complexity. Let's try it in a code editor.
If getting your learning started is half the battle, what if you could do that for free? Visit Skill Up by Simplilearn. Click on the link in the description to know more.
Let's start with the string braces food, which is equals to in braces in curly braces first element as pie, comma soup, comma sandwich, comma pizza, comma juice. Now let's write a for each code where in argument I will write string I in food and then we will write console dot write line then I. Let's save it and run it. It should print out each and every element. And as you can see, it is printing out pie, soup, sandwich, pizza, and juice. Let's get back to our slides. Next up, we have n log n complexity. An algorithm with a complexity of big O of input size n, where n is a really big number. It divides the problem into little chunks for each invocation. Then takes each of the smallest bit and stitches them back together for n log n complexity. To execute a given operation on n items, it takes n log n steps. Typically, a quicksort algorithm shows the properties of big O of n log n complexity. Let's write up a code to explain quicksort. Let's start with a simple function static public int partition, where arguments will be int arr, comma int left, comma int right. Then we will define a variable int pivot, then this pivot will have array at left, then while It's true. I will have another while loop. Array at left is less than pivot. Then we will have left plus plus. In case while ARR at right is greater than pivot, then we will have right minus minus. Now if left is less than right, then int temp will have ARR at right. ARR right will have value of ARR at left and ARR left will have the value temp. Basically we are only switching these values. Else we will return right. Then we will have another function static public void, that is quicksort, with argument as int traces ARR, comma int left, comma int right. I will have int pivot, then if left is less than right, then we will have pivot is equals to partition with ARR, comma left, comma right as argument. Now if pivot is greater than 1, then we will call quicksort with ARR, comma left, comma pivot minus 1. Or if pivot plus 1 is less than right, then we will call quicksort with the argument as the same array, comma, pivot plus 1, comma, right. Now let's come back to our main block. Let's start with writing int an array equals to, let's take values as 56, 21, 59, 65, 58, 100, 32, 6 and 9. Then let's have another variables as int n equals to 10, comma, I. Then we will have console dot writeLine and print quicksort. Then a console line dot writeLine let's print the initial array so for that we will write a for loop I is equals to 0, I less than n, I plus plus. So console dot writeLine arr at ith location plus a space. Then let's use quicksort for array from 0th location to 9th. This will sort the array. So now console dot writeLine sorted array. Another for loop with I is equals to 0 to I less than n to I plus plus. Then we have our console dot write array at I plus space. Let's save it and run it. As you can see, it is first printing the initial array, then it is sorting the array. Now let's get back to our slides. Next up is quadratic complexity, a method for input size n where n is a very large number, executes almost double or n squared the steps, and the algorithm's time changes. The complexity of method is stated to rise quadratically as the input size increases from n square. For a particular operation, it takes the order of n square steps, where n is the size of the input. When the number of steps is proportional to the amount of input data, then we get a quadratic complexity. Here is a simple program of a nested loops, which in turn gives us the n square complexity. Let's try this in a code editor. Let's start with the nested loops. So for loop and I is equals to 0, I less than 4, I plus plus. Then we have another nested for loop and j is equals to 1, then j is less than I, then j plus plus. Basically, this is letting us to run this loop only 3 times. So let's have a console dot write line let's write subscribe to Simplilearn. Let's save it and run it. Let me clear the logs. As you can see, it is printing it 3 times. Let's get back to our slides. And this was all for today's session. Hope you guys found it informative and helpful. If you liked this session, then like, share and subscribe. If you have any question, then you can drop them in the comment section below. Thanks for watching and stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.